Good evening, everyone. My name is Shurui Miao, so the last name is pronounced exactly like how cat make noises. So today I want to share a bit about my work at Oxford, and big thank you to Saskia, Izzy, and all the ambassadors for this opportunity. So I want to start my talk with a little question. So here on the slides, if you have read abstract, you would know the answer to this. So here on the slides, we have some amazing architecture in the Vatican City and some amazing natural scene in Italy. So I was wondering, can you think of what's in common between the two? Any idea? Yes? Exactly. They're both made of sediment rocks, which are a form of carbon-containing minerals. So that's the core of my talk. Okay, so we're going to talk about, well, our work is about understanding the process of how gaseous CO2 in air turn into rocks as a way of securing and storing CO2 as a method or solution to combat climate change. So a very brief journey of how I got here. So I actually did all my higher education in Australia, well, including secondary education. So I spent past 13 years in Sydney, which is amazing, and then came over as a postdoc in 2023, and now I am a research fellow at the Department of Chemistry, as well as hosted by St John's College, Oxford. So I'm on dual mission here, so at least I assign myself dual mission. One is to show you the interesting science that I do, and the other is to sell Australia to the audience. So please, so you can see that my talk is roughly divided into 4 sections, and each of the section will be broken apart by a set of images of Australia, and I would love to answer any questions about Australia as well. So in terms of the scientific content, so we're going to start with the context of our work. So why we're interested, what are we looking at, how is this relevant to climate change, and then we're going to introduce some scientific concepts and experimental setup that we designed and built in order to study them, and then finally finish with some results, implications, and sort of a short list of opening questions that we sort of still needs to be addressed. A little bit more about my sort of discipline or area of expertise is that I am a physical chemist. So Joe briefly mentioned that chemistry can be broadly defined, subdivided into 3 sections, which is the structure of Oxford Chemistry Department. So I am part of the physical chemistry. So unlike organic and inorganic, which are geniuses and experts in making new materials and drugs and to sort of realize new functionalities, the physical chemistry section is about making new measurements and understanding how chemistry change as a function of physical environment, or in other words, how chemistry interact with the physical world. So we're trying to study how chemistry processes affected by pressure, temperature, in our case, confinement, which is how when we reduce dimensionality. In the bulk, in this room, we're in a 3-dimensional room, but let's say, some strange reason, imaginary world, that the ceiling start to fall down, that we're all going to be compressed into a 2-dimensional world, and how does that affect the chemistry? So that's basically where I come from. So towards the end, there'll be slightly sort of challenging math, but I'll walk you through it. So the take-home message is to trying to understand what we do and trying to understand how we can connect to the climate change and be part of the solution of the climate change. So as promised, we're going to start with a little bit of context. So this is just a very brief reminder of where we're at about climate change. So I've taken some graphs from the IPCC report. So this is slightly outdated, but you get the idea. So on the right panel, there is global emission on the y-axis and a timeline on the x-axis. So you can see the black line, it's the data points that we actually have data of, and then the red, green, and blue are projections based on various models that they simulate emissions, human activities, weather system, etc. The key thing here is that with all the implemented policies, so this includes all the national commitments, let's say Britain want to be net zero by 2050, European Union want to be net zero by a certain timeline. So factoring all of those in, we are really following the red curve. Okay, so that's looking at a 2.2 to 3.5 degrees increase by the end of the century. We're talking about an average global temperature, not talking about a particular summer day is 2 degrees warmer. So that's horrifying or scary. And by that, we're looking about 50% loss of biodiversity, and we're going to be expecting a lot more frequent and severe climate disasters. Whether it's the super typhoon that just landed in Asia yesterday, or whether it's the wild bushfire in France this summer, all of those will be more frequent, and that's going to be a huge societal, economical impacts. So if we're to stick to the Paris Agreement, which is to limit climate change to 1.5 degrees by the end of the century, then we're really looking to forward the blue curve. And you can see that if we are to do that, we require almost a cliff-like turning point. And that's really, really difficult to realize. So the message here, what I'm trying to highlight is that yes, reducing emission is important, but we really need to already start thinking about how do we remove CO2 from air, not just slowing down our emission. We have to have a way to store CO2, take CO2 from air, and remove it, store somewhere so that we can mitigate climate change and climate disasters. So although that's all sort of slightly daunting and scary, I also want to highly recommend, by the way, no financial interest, this particular book that I just randomly picked up at the airport. It's really an amazing book. It talks about where we're at with a lot of societal challenges with data science. So the real numbers. So for example, although we're talking about a very stunning, sort of scary statistic here, but the good news is that per capita, global per capita emission, so per person emission average globally, already peaked in 2012. So we are on a good trajectory to solve this problem. We can be better, but we are on a good trajectory to solve this. So it's not the end of the world, as the title suggested, and I highly recommend this book. Coming back to the science, so building on that not end of the world message, there are innovations coming up around the world that trying to sort of, again, thinking about storing CO2 securely. So one initiative is called Undo. It's a startup company based in Sheffield. So what they do is they take all the byproduct from mining, which are often, things that doesn't contain precious metals, but rich in calcium, magnesium, etc. What they do is they grind it up to increase surface area and sprinkle in farmlands. And that increased surface area brought into contact with our atmosphere, so it passively absorbs CO2 from air. So they're talking about a life cycle of 10 years. What I mean by that is that every 10 years you have to reapply these dusts, and they will fix X amount of CO2 over the course of 10 years. The benefit of there is that all the infrastructure is available. Right now, as a part of the agricultural industry, we have to regenerate our soil due to our intense farming activities. We have to feed the soil with essential nutrients for the plant. So this is essentially that practice, but also at the meantime fixing CO2. But this is the drawback of this technology is that it's a passive thing. It relies on rain, it relies on weathering, hence carbon mineralisation is often referred to as enhanced weathering. That's the term that news tend to use and some scientific papers. The second technology I want to highlight is sort of a European Union initiative which is called CarbFix, which is joined with Climework. CarbFix really monitors sort of the storage side, sort of the very far right of that image. Climework really do the direct air capture side of the things. So essentially, it's built on a similar idea. So you mix water, CO2, sparkling water, and then you pump underground into volcanic rock layers that are porous with a lot of surface areas, rich in magnesium, rich in calcium, and then you let nature take over. So the bottom chemical equation is thermodynamically favorable. So it will spontaneously happen. But under ambient room sort of lab condition, the reaction rate of this reaction is so slow that it's irrelevant for society. We're talking about thousands of years. So you don't see a mountain building up overnight. But on geological timescales, this is just how nature deals with atmospheric CO2. So really the idea here between both of these technologies is to accelerate that process by some human intervention. And so we're going to focus on CarbFix because it's sort of a more active way. We're injecting CO2 and water underground, and the life cycle, sort of the half-life there is about not half-life. What they do is they call it that they achieve 95% of mineralization in 2 years. So that means 95% of whatever CO2 they pumped it down have turned into secure, stable minerals in 2 years. So that's now much, much more relevant to tackling climate change. So a little bit of a sort of scalability analysis. So on the far left of the screen, you have that purple stream of sparkling water injecting into the basaltic rock layer and then forming those wide sprinkled crystals. So that's the CarbFix technology, the injection of CO2 and water reacting with volcanic rocks, forming mineralization. On the sort of next to it, the pink sort of schematic is showing the state-of-the-art industrial approach, which is to pump to extract CO2 and then turn it into a liquid, liquefy it, or make it turn into a supercritical fluid, so pure CO2, no water, and then you pump it under some sort of a capestone or sort of a capped rock, which is impermeable to CO2, and that means CO2 cannot escape. So it's kind of like brushed dirt under the carpet. It's trapped there. And obvious question there, or problem there, is that if there's any like earthquake or geological movements, if there's a fracture, there's a leak, then all that CO2 can readily escape back into the atmosphere. So it's not a permanent solution. And the other benefit of the mineralization is that scientists have done, well, earth scientists have done abundancy analysis and combined the purple and orange areas together, which are places ideal or suitable for mineralization. We have more capacity basically under those colors than the amount of emission if we combust all the CO2, combust all the fossil fuels that we have discovered so far. So really, what we're trying to say is that we have the capacity to absorb, to fix all the CO2 that we are already emitted and we are going to emit. So that's why we're interested in this technology. And as a quick proof of concept, so we went to our colleagues in earth science here in Oxford, and they gave us a little sachets of volcanic rock. And what I did is just, old pestle mortar, grind it up, put onto a SEM stab, and that stands for scanning electron microscopy, which is a tool to look at very, very small things and be able to resolve elemental distribution. So you can see the black and white picture of the top left corner, that's basalt, that's the raw image, and then all the colored bits are basically showing you the elemental distribution. So what I'm trying to highlight here is that it's a silicate mineral, so silicon oxide mineral, but with magnesium, calcium, ions basically evenly distributed and abundant throughout the mineral. So this is a good sign because the bottom row, the three elements on the bottom, they are good at reacting with CO2 and bicarbonates to form CO2-containing minerals. So what I did is I added a drop of water. So remind you that essential ingredients of this chemistry is CO2, water, and some divalent cations, so calcium or magnesium. So what I did is I added a drop of water, left it in room conditions, so exposed to air, which has about 400 ppm of CO2. And then come off the sort of a day later when evaporate all the water off, and then I get nice crystalline calcite formed on the surface. So this is just a quick proof of concept I did in the lab to convince myself that this is a worthwhile pursuit. And of course, that people have done much, much more rigorously. So people that work on this technology and building plants in Iceland, what they did is they drilled sort of cores underground, about 800 meters underground, and then imaged and trying to analyze how much has been mineralized, what's the porosity of the rock, etc. So as you can see on top there, so that this is a cylindrical core. The diameter of it is about, I think, 4 or 5 centimeters. So it's really a sort of an arm-sized core that they draw up. And then you can see here there's some white specks forming at that crack between the two right and left layers, and that is calcite. So that is mineralized CO2 after injecting. So here I have a tiny challenge for you, which is I'm going to show you a block of calcite here, if technology works. Oops, completely missed it. Here we go. No. Hello. Oh, here we go. So this is our colleagues in earth science has kindly supported provided a sample. So you can see this is a size of my fist. Put next to it. So it's about the size of my fist and weighs about 400 grams. So the challenge to you is, can you guess how long it would take for someone, so based on global average of today, to emit the equivalent amount of CO2 of this block of rock? Okay, so the hint is that look for the star throughout the slide. So as I talk, I've sort of estimated how long I will talk and then mark the star. And as soon as you see the star, that's from now till then, that's how long it will take for each of us to have emitted amount of CO2 that can generate one of these. Okay? Now, by saying emitted, I'm not talking about breathing. That's actually a very, very small fraction of our emission, our footprints. All the clothes that we wear, how you came to Oxford, all the technology that's enabling me to talk to people online, all the email you send, all the text you send, all of that included. That's your daily emission, okay? So keep that in mind, and let's proceed to some beautiful pictures. And I should get this back. So before I move into the next section, so just, as promised, some beautiful pictures of Australia. On the right, or on your left, there is Whitsunday Island, often the sort of ranked the most beautiful beach in the world, just off the coast of Queensland. And Uluru, it's a gigantic monolith of sandstone in the center of Australia. It's sacred to the native indigenous people, and you can see this amazing, charming orange color during sunset. Smooth. So we're now going to talk about some fundamental physics. So quickly reminder that we have positive and negative charge in the universe, and the opposite charges attract. If you have positive, positive, or negative, negative, they repel. So that's the basic concept that we're going to start from. Now, slightly complicated. So if I have now an interface, so if I have a solid surface that carries negative charge, that's what the blue slab is representing, a solid that has negative surface charge. And then now it's in contact with a solution that contains some salts that have some dissolved iron in it. And then this is sort of my cartoonish representation of how the ions would distribute as a function of distance from that surface. So remind you that negative charge attract. Next to the negative surface, you're going to have abundance of cations. You're going to have abundance of positive charges. But then positive charges repel each other, so they will have some negative scattered in there to buffer that repulsion. And then that decays. The density of positive charge, sort of, you can see it's very high close to the surface and decays further and further away into the bulk macroscopic concentration of ions. So this is what we call a model of the charge interface. Now, I mean, physical chemists, right? We like curves. We like pictures are beautiful, but at the end of the day, we want to represent it onto two axes. So we have distance of the interface, and then we have the magnitude of effective charge, so you can just treat that as a number of positive charges. And then what I'm plotting here is that you see an exponential decay, or as we already mentioned earlier, you see this decay from very densely populated positive charge to less dense populated to eventually the bulk equilibrium concentration. So how much salt in the water. So this is what we call a screening effect. So all those positive charge are basically there so that they counterbalance the negative charge of the solid surface. So that if you are infinitely distant away from the negative surface, you won't feel its presence because all its effective charge is screened by ions in the solution. Now, this screening effect is, of course, dependent on a number of ions in the solution. So if I increase salt, which means adding more ions into the liquid phase, then you see this decay becomes steeper. So that means the charges of the solid interface, of the solid surface, is screened more effectively by the solution. So now I can become closer to the surface, but still not feel its presence because I have more ions in the solution to screen it. Now, we have a jargon for that. So this decaying envelope of effective charge is what we call the electrical double layer. And if I have two electrical double layer, so now I'm bringing the concept of confinement. So if I have two electrical double layer, and if I push them together, so here's a tiny animation, if I push them together, as soon as they start overlapping, they start to feel the presence of each other. And that makes them uncomfortable. They interfere with each other, and they don't want to be there, and that's measured as a repulsive force. So we already mentioned that if we add more salt, we increase the ion concentration, we're shortening, or we make that screening effect stronger, so we sort of reducing the electrical double layer, which means the surface can be brought together closer without repelling each other. So that's sort of the train of thoughts I'm trying to build here. And how is this relevant to mineralization? So come back to CCS is carbon capture and storage. So coming back to how this is relevant to mineralization is that we are injecting carbon-containing water into a porous medium. And those pores has a range of size, an array of size from micrometers down to nanometers. And being a pore means that you're at least surrounded by two surfaces. If it's a cylindrical core or if it's a cubic core, then you have four solid-liquid interfaces. And then the interaction between those surfaces become important because that dictates how much iron can be in the pores and how willing they are to stay there, and and that subsequently will affect how the process of them nucleating, which is a term of solvator species turning into solid. So that governs the first bit from the blob into a crystalline, which is represented as a square here, and also governs how the mineralized particles interact with each other. So all of this interaction is governed by the screening effect, which is in turn dependent on salt concentration or iron concentration, and as well as the geometry. So that's the picture I'm trying to build, and that's exactly what we study. So the technique we use to study these is really, really straightforward, and it's very elegant. So on the left is a s'more, which is 2 pieces of biscuits. So this is a classic campsite snack. So you have 2 pieces of biscuits. You have a chocolate, whether you like or not, can be omitted, and then you sort of roast the marshmallow, and then you squash them, make a marshmallow sandwich, and that's exactly how I do science, but much, much smaller. And remove all the excitement of the campfire. So if we make this 100 million times smaller, so I assume the cracker is about 10 centimeters in diameter. So if we make them 100 million times smaller, we're down to the molecular scale. And that's what we're trying to do. We're trying to make a molecular sandwich and measure how the molecule resists the process of turning them into sandwiches. If you're having difficulties of grasping what 1 nanometer is, please join me to stare at your fingers for 1 second. So just look at your finger for 1 second. Good, perfect. And so in 1 second, how long your fingernails has grown is about 1 nanometer. So over the course of 1 second, all your fingernails have grown by 1 nanometer. And that's sort of the resolution we want. We want to measure that. And we want to measure the force behind that. Okay, so before delving into the scientific details, I'm going to show you some beautiful pictures of flora and fauna in Australia. On the far left, we have a very cute and gentle Australian sea lion, severely endangered but bouncing back, very gentle. They're very well protected, so they're not afraid. You can get quite close. I mean, you're not supposed to get too close, but you can. Quokka, unfortunately, I haven't seen one in Perth yet, as in I haven't been to Perth yet. But they famously live on a remote island without predators. So they are curious and friendly beings that they love to take selfie with you. And then green sea turtle, maybe, because I'm not an expert in recognizing animal species, but it was a lovely opportunity for me to snorkel along Great Barrier Reef. And then sea turtles, again, very gentle and curious creatures. They would just come and gently float next to you. Great. Back to science. So I previously mentioned that my job is about making those molecular sandwiches. Now, how exactly we do that? So it's very tricky because the resolution we want is so fine and the forces we're trying to measure is so small. So what we do is that we have 2 cylinders. This is just for practical reason to simplify the experimental setups, and then setting on springs. So this is essentially like how you weight your apples and bananas in Tesco. If there's a force between the 2 surfaces, between the 2 cylinders, then the spring is going to deflect, and we measure that deflection and convert that into a force by Hooke's law. So you can see on the very bottom, there's a tiny equation: force equal to spring constant times by deviation. So that's what that is. It's just Hooke's law. But to resolve those tiny changes in distances, we resort to interferometry, so white light interferometry. So we use white light, which is provided by the land, by the projector. In our case, we want it to be a very well-defined wavelengths, very well-defined intensity, so we use a laser. But in general, it's just the white light. And what we do is that we put some reflective surface on the 2 cylinders so that light can bounce between them. And as light bounces between, it interferes with itself. So it generates a unique interference pattern that depends on the separation of those 2 mirrors. So that's basically the technology we rely on to resolve very, very small distances. And then what we just do is just squash them. We squash them with our sample in the middle, and we measure deflection of springs and interpret that force and try to make sense of it and relate that to other observations. So coming back to the point that we're trying to resolve molecular features, that means our surface has to be extremely, extremely smooth. So if you imagine I have a very bumpy surface, then as soon as the roughness of the surface are touching each other, I'm going to lose all the spatial resolution because I'm just going to measuring the surface rubbing against each other. So whatever smaller features than the surface roughness is basically undetectable to us. Okay, so for us to resolve molecules, the best molecule, the sort of the holy grail for us to resolve is the water molecule, which is about 0.3 nanometer in dimension. So in order to resolve those tiny, tiny structures and molecules, we really need the surface to be atomically smooth. We need it to be as smooth as possible, the most smooth object you can imagine. And that will result to, again, nature. So nature has a mineral called mica, which you probably come across into sort of on your hikes, that you'll see these shiny disc-like, very slippery surfaces, which they are just, so this particular mineral is, they call it a lamellar structure, which means you have layers of crystal structures on top of each other, very sort of parallel to each other, like a lasagna in a sense. And then what we do is in the lab is that we, in a very well-controlled environment, we're sort of trying to peel each of the lasagna sheets. We want a very clean and sufficiently big sheets so that we can put it onto our cylinders as our effective surface, and therefore these are atomically smooth, and we can use them to measure molecular features. So with me talking all of that, the sort of the thinking and design behind the technique, I just want to quickly show you a real-life experiment. So this is real-time, but 10 times faster, because otherwise we'll be here for a while. So you can see it on the top, the white bands are moving. That's the diffraction pattern that's changing over time, which is a sign that our surfaces are getting closer and closer together. And then now the surfaces start repelling each other. So at the start, you see the motion is linear with time. So that's when the two surfaces don't feel the presence of the other. There is no force between them. And then you see it slow down. That's where you start having repulsive force. That means we are still applying the same motion. We're still driving them at constant speed, but then they are refusing to get closer. So that's a repulsive force that we're picking up. And then eventually, that it has accumulated enough force that we get this tiny blip here, and that is a molecular feature. So in this particular experiment, it's not, but in the past we have resolved, so in the same, qualitatively the same shape and things like this, a water layer, which is a 0.3 nanometer. So I'm just gonna play that again. So, oops. So I'm just gonna play that again. At the start, it's linear all the way, still linear, start sensing each other, start repelling, and then repulse a little bit more, and then break the threshold. So there's a little step jumping, which we can basically, by analyzing the image or the video, we filmed the entire thing. So it's slightly embarrassing to admit that how long I've spent watching these videos. I mean, they're just so exciting for me. This is the first time ever after sort of in my career that I get to visualize a molecule. We're just sitting there looking at a screen. I get to see the dimension of individual molecules, and that was super, super exciting. Anyway, so coming back to how we treat or analyze this data, as I mentioned, at the very start, we're applying a linear motion. So that's what the blue line is. So when the surfaces are moving close together as a linear function, so proportional to time, then we say they're not sensing each other. They're not repelling each other. They're not forcing. There's no force between them. But then as soon as you can see the purple line deviates from the blue, that's where the repulsion starts. And that's why we start measuring a positive force on the right panel. Okay? And then the little jumping, we call it the little step change, we'll also observe in the step change. So we know how much force we have to apply, in the most naive sense, squeeze out a layer of molecules. How much force we need to apply to squeeze out a single layer of molecules. That's amazing. Now, so interpretation gets a little bit messy. So I just want to show you some benchmark system at the start. So on the left panel is the pure water we typically refer to in the lab. So that's a molecule water, which is filtered through various technologies to be as pure as possible. And then we measure, we squeeze them between our mica because this has a very low concentration of salt. It has very few ions. Therefore, the forces, the surface staff feel the presence of each other very, very far away. So previously I showed you that the little force kicks in around, I can't really remember, but around tens of nanometers, but this extends all the way to up to hundreds of nanometers. So we're talking about the left panel there. So the two surfaces will sense each other when they're about hundreds of nanometers apart. I mean, it's still a tiny number, but to us, that's a huge range, a long range repulsion. So that we understand, that's exactly what we expect, and we can calculate the effective ion concentration in water, and that matches exactly to how much CO2 we dissolve in water under ambient condition. And then on the right-hand side, we have a panel where we deliberately added a lot of salt. So in this case, magnesium chloride, so we added 0.24 molar of salt. So that's 0.24 moles of salt per liter of water. And then we have no measurable decay links. And what that means is that the two surfaces basically don't see each other when they're even next to each other, because there is so much salt, so much iron in the liquid, that the surface charge of the surface is screened within a very, very small distance, that they not be able to see each other until they're physically rubbing shoulder against each other. So that's why you see basically a flat line and then a very sharp increase. That sharp increase is when they're physically rubbing against each other. So you can see the characteristic difference between them, and they are both classical in the sense that we know how to interpret them. They are same as our expectations and matches our understanding of the solid-liquid interface. So I've showed you that. Now it's a more a theoretical depiction of the exact same idea. The classical theory we refer to is called a DLVO theory. I'm happy to chat more about it afterwards, but we're not going to dive into detail of this. But essentially what I'm trying to show you is that with more salt, you see that repulsive, so that uprising, the little peak towards the left-hand side, is decreasing in magnitude. As you increase salt, it becomes lower and lower, lower, lower. Eventually, in the blue curve, there is no peak anymore. So there is no repulsive interaction between them anymore. So that's the feature I want you to remember, and this is how we compare to experimental data. So I want you to focus on the blue and the yellow. So blue, if you look at the legend, it's about 0.01. Yes, 0.009, so 0.01 moles of calcium chloride, so that's a low concentration salt, and we're already not seeing any repulsion. So you can see the purple line, purple solid dots underneath the big blue open circles. The purple filled marks are it's the exact data set of the magnesium chloride showed on the previous slide. Okay, so I'm just using that as a reference. So what I'm trying to show is that all the repulsive force between our surfaces is effectively screened by 0.009 moles of calcium chloride. So if I increase the concentration of salt further, that means that's not going to do anything. There's nothing more to screen. The screening is already being done by a very dilute solution. However, that's exactly the opposite is what we observed. So when I increase the concentration of calcium chloride to 0.28, so comparable to the magnesium solution, I actually retrieve this long exponential decay profile. And that's bizarre because that means our understanding of the electrical double A doesn't make sense anymore. So there is a puzzle there. We're trying to understand what's going on. And before I tell you the answer, some more pictures of Australia. This is a little bit bragging, but on the very left-hand side, it's just a random beach in New South Wales. One day you drive an hour from your home, this is where you get, and this is what we call a beach. Miles and miles of fine sands with only one surfer there that day. And then the Stewart Highway, which is often rated the most alien-looking places on Earth. A lot of sci-fi movies are filmed. You get this long, straight, narrow road connecting the two states and territories of Australia. And then on the rightmost is Lake Tyrrell, a representative of a family of pink salt lakes in Australia. And the caveat is that when I was there, this is actually what I saw. So I had to resort to internet to get a pretty picture. And I don't know if you notice, the star is showing up, okay? So it's roughly about 30 minutes that each of us, according to the global average, will emit enough CO2 that's going to mineralize into about 400 grams of calcium carbonate there. So that's basically our job. I mean, that's basically what I'm hoping to do, right? To convert all that emission back into rock. So you can see there's a very dense and stable form of storage available to us. I mean, that little blob, it just sits there and it will be stable for thousands of years. And that's fine under room condition. It's not going to go anywhere. It's not going to re-escape into the atmosphere or anything. Yeah, so now into the final section of what our data actually tell us. So this have to sort of look into the literature again and borrowing some concept. So I want to introduce the nucleation mechanisms. So the classical nucleation mechanism is depicted by the very bottom direct arrow, which is atoms, ion pairs, molecules come together to form a crystal. The crystal grows basically by atom at a time. So each atom will attach to the surface, become part of the surface, and then the next one comes in, and then it grows slightly bigger. So that's the classical view of individual atoms coming together to form crystals. Now, since the advancement of characterizations and physical chemistry techniques that we now understand, especially in biology actually, there is an array of non-classical nucleation mechanisms. So on the very top, the very big arch is called a nanocrystal-orientated attachment. And that's almost like piecing Legos together. So what that means is that individual atoms will come together to form tiny, tiny crystals, and those tiny, tiny crystals in solution somehow sense each other and orientate each other so that when they collide, they form a single crystal. So this is fundamentally different to the bottom process because we're not talking about a nanocrystal dissolve, disassemble, dissociate into individual ions, and then reattach onto a different crystal. That would be the classical picture. Instead, the non-classical approach is that each of those nanocrystals can sense each other and align and then come together as a single crystal. So this is important because all of this, different mechanism will have different governing factors, will have different kinetics, will have different tools available to us to control the rate. Again, coming back to the context of carbon nucleation, we really want it to be cheaper, faster, more energy efficient. So understanding the nucleation mechanism is fundamental to the scalability of this technology. So I've said all the good things about the technology. The drawback is that it is still not economically viable, as in it's not a profitable business yet. So there are lots of plans around the world, but they are all subsidized by government initiatives. So how to make this process profitable so that really the industry take it up relies on our understanding of how to make the nucleation process favorable, fast, and energy efficient. So now it comes to the scientific paper searching. So this slide is very dense information. What I really would quickly point out is that there is an ongoing debate, very sort of a hot debate in the literature about what is the underlying mechanism of calcite mineralization. It's not only important for carbon storing, it's also important for our understanding of why shellfish make their shells and how they make their shells. So carbonate is really everywhere you look in the biosphere. So the debate is sort of led by two groups of scientists. One of them says that, so the picture is just the evidence. I really want to focus on is the text underneath. So one group of scientists says that we have hydrated ion clusters. And what that means is that each ion is solvated by a bunch of water molecules in solution. And each of those solvated ions somehow cluster together. So as a result is that instead of free ions, instead of each of the ions being free to be explore whatever, do whatever, including conducting electricity, they now sort of aggregated together, become a big chunk, and that doesn't conduct electricity so effectively. And that's what they call the pre-nucleation cluster. So the evidence is that if you look on the top panel of this plot, the red line is the expected conductivity of solution over, here it is on the time axis, they actually continually adding more salt. So over concentration. So essentially the red curve says that if I add more salt, the conductivity of the mixture should go up. And then the black line is what they measure, and they see this deviation at a very, very early on stage, even way, way before saturation. So that's the evidence, that's a sign that something is happening even in the very dilute solution that prevent these ions from conducting electricity. And that's why it's sort of supporting the idea of we have these clusters, aggregates of hydrated ions, even at very low concentration. Now, the other school of people saying that nothing beyond ion pairs can exist in solution. I mean, of course, backed by evidence and simulations and lots. So again, pretty pictures, but the key takeaway message are the bullet points. So they say nothing beyond ion pairs. So cation anion is what we call the ion pair. They are stable because, again, the opposite charge attract. So nothing is beyond ion pair, so everything can be explained by ion pair. Instead, what nucleation of calcite or carbon minerals is that once you pass the saturation, so this is where a point where thermodynamically your solution is no longer stable. Some crystallization will form if you give it infinite amount of time. So that's what saturation means. So what they say is that dense ionic liquid droplets are present in the supersaturated concentration. So if I continue to add salt above the saturation point, then I start seeing these blobs, liquid-like blobs, that's rich in calcium and carbonates forming. And they are the precursor of turning into crystalline materials. The difference between these two is basically, there I have large charge correlated structures even way below saturation, and then on the right is that only exist above saturation. And of course, the clusters will have different physical properties that we can probe, and that's exactly what we're trying to interpret our measurements. So as I sort of warned a little bit early, we measure these data points, and then at the end of the day, to understand it, we have to sort of fit a theoretical framework to it, trying to extract a physically meaningful parameter. So ignore the mass. What I'm trying to say here is that the purple line is our experimental data, the black line is not a great fit. Okay? And the black line corresponds to a mathematical description of what will happen if pre-nucleation clusters, these hydrated clusters, are present in the solution. And on the right panel is that, now again, the black line is the fit. So this is the dense liquid droplet scenario. So it's a different set of equations that we'll have to use to fit and play around. But you can see it's also not a great fit. So what we're seeing here is that we are getting some very counterintuitive measurements in our study, and then neither of the two sort of leading theories of nucleation mechanism gives a good enough description to our data. And the reality is likely to be between the two. And so that's where the work in progress comes in, is to understand, can I reliably fit this and understand them a bit better? And this is sort of how we connect our measurement, although, like I said, physical chemists like to have these 2D scatter plots. Although at the end of the day, after all that hard work, we just generated 2D scatter plots, but by fitting it with a mathematical model, our physical understanding can be enhanced of real processes that's relevant to carbon capture and storage. So just to echo on Joe's comment about that, no scientist, it's not a one-person game. So I am, of course, also supported by a fantastic team here. So on the left is the photo taken recently at a host group from our group. So it's without a pointer, it's a bit hard to see, but you can see Susan in the far left corner. And then the rest, the postdocs, PhDs, and master's students in the group. And of course, science needs funding, so very thankful of all the funding agencies, especially St. John's College for providing the fellowship. And thank you very much for your attention. I would love to answer any questions.